Okay, um, so here's our first analysis of the first system. If you notice the page number in the lab manual, and this is the lab manual file that you received, this is page 12. So the pages that are referred uh, on the schedule of classes are the page number. It's on the lower corner of the lab manual page. It's not the number at the top. If there would be any number in the top, is the handwritten number, like for example, this is page 11 and this is page 12. So this first system does not have the name of the system on the page, but this system is called limited memory. And actually it has two diagrams, kind of pressing of what's happening. So we will use this diagram first, and then I will switch to the actual lab report to show you the color coding and everything. So that will be our routine. I will show you first the system in the lab manual so we can trace analysis of how the system works, and then you will see we'll go to another analysis that are already from the report with color coding, so you understand how the analysis was divided in stages and how the color coding works. Okay, so if you look at this at this system, you see that components are indicated by just writing on the diagram. So this is not the best. This is not the best technique of using it, because once you have more components, then your diagram is all over. You have to write many components names, and sometimes those names are multiple. Like for example, if you have MAV3 valve, so that's MAV3, you could refer to it also as a three-way valve, normally closed. When you have flow control, you could say is MFC2, you could see the flow control, and so on. So this is not practical, and I'll show you later on the report how it was done, that basically next to the diagram, each component has a unique number, and then those numbers indicate in the table of components what those numbers refer to, what kind of component. And let me just go quickly to, for example, system which is two-hand no tie down circuit. Over here you see only the number of components over here, and then there is a table of components in here, and it says what component number, what model number, what type of valve it is, and so on. So when you look at the number and you don't recognize the component from the shape of it, then you can confirm with the table of components what this component is. Actually, on this diagram, it's also not the best way because of naming the component. As I mentioned, that each component should have a unique number. And as you can see, number 1 is assigned to 1, 2, 3 valves. And later, it may be a confusion which referring to those components in your analysis. Because if you say that valve number 1 was activated, which one would you refer to? You would have to refer the valve number 1 on the left, in the middle, on the right, and so on. And that would be confusing. So So later in the report, you will see that each component would actually have the unique number. So in your analysis, you can just write down number 1 was activated, then the pressure was passed, let's say, to number 2 and activated number 3. In your analysis, you don't have to further describe what kind of valve it is, because on the diagram, it's already described in table of components, and you don't have to further describe, because that will be double or triple description. You just say number 1, and it will be clearly visible from the diagram what number 1 is, okay? In this case, you see it's PB1, PB2. So even though you name it 1, then you have a second description, push button number 1, push button number 2. Over here, you have RV, 2 valves. Or shuttle valve 1, shuttle valve 2. So there is no reason to do that, because it doesn't help your analysis, but rather adds the confusion which valve you activated. If you, instead of naming both shuttle valves number 4, if you name them, let's say, 7 and 8, then basically you say, and the pressure goes to the right side of number 7, and then goes farther and activates the left side of number 8. And you don't have to add extra abbreviation SV1 and or SV2, okay? Because those are not former names anyway, because a shuttle valve is MSV1 as a model, and SV1 or SV2, that's something that you made, it was made up, so it shouldn't be included in the official report. Okay, so let's look at a limited memory. And since our first two systems that we analyze are the full memory, and then the other one is limited memory, after we analyze both systems, I will describe or tell you what memory refers to. Why is the first system that we analyze limited memory and the second system full memory? Okay, so in your system, and if you have any questions, just let me know. But it's good also to have handy, let's say, I will show you what you should have handy, which file, and you can open it on the site, is this file, pneumatics and hydraulics. Oh, sorry. Actually, that's not that. That's this handout. And in this pneumatics and hydraulic handout, you have the description of analysis of all the valves. And from this handout, you can also open reference to given valve if you don't remember how it works, and you can go back between the handout and between the analysis, between the diagram of the system we analyze, and then you will understand how the component work. Okay, so let me stop sharing that and go back to our system. So this system has 2 3-way valve MAV3 as indicated here. This one has the stem exposed, and the stem of this 3-way valve is inside the actuator. There is also a flow control valve, and note that if the knob of this flow control is on the right side, it means the arrow points to the left. So the pressure is being controlled from the right to the left only. the pressure from the left to the right has a free flow. So it's not being controlled by the flow control. And just for the general purpose of analysis with the flow control, let's say if the knob, position of the knob, number 1 would be fully open and number 10 would be fully closed, then let's assume we are like about 8 or 9. So meaning that the knob is almost closed, but still allows some pressure in. And being almost closed will help us to understand what's the purpose of the flow control. If you have a flow control fully open, then it wouldn't be any difference whether the pressure is being controlled to the right or to the left, because it will be a free flow. So let's assume that whenever you have a flow control, is almost closed, but still allow the pressure. So for analysis, the pressure with the direction of an arrow on the flow control, and in this system would be from the right to the left, it's flowing slowly, okay? But against the pressure against the direction of an arrow, which is in the system pointing to the left, it's a free flow. We have MAT50, which is actually MAT.50, meaning that the volume of this tank is 0.5 of cubic inch. And we have an output component, which is a spring return cylinder. As I mentioned before, the connectors, such as these, they don't have to be indicated on the diagram. But when you look over here at the top junction, that would be a splitting into 2 ways. And also at the bottom junctions, that will be splitting in 2 ways as well, coming from the compressor and splitting to the top, to both 3-way valve directly from the pressure source. Okay, and of course, hoses are in between, connecting all those components. So pressure about 40 psi, which is a standard pressure for any of our systems. And this pressure comes from the compressor, and it will be in the lab indicated on the Bourdon gauge, which is at the beginning of the system. So you would set the pressure and you would log this pressure to have it for the entire duration of the analysis. Okay, so the pressure comes to the bottom of the 3-way valves. The way that the 3-way valve works, and actually let me actually bring the pneumatics handout. So I will remind you, just because this is the first analysis, so most likely you may not know by heart all those components. So I will show you the 3-way valve, MAV3, which is normally closed. So here you go. The way that the 3-way valve works, if you provide the pressure, and on our diagram of the limited memory system, the pressure comes to the bottom of the valves, both 3-way valves. If the pressure is provided at the bottom and the stem is up, the pressure is not passed anywhere. It just waits for the activation of the stem on the valve. Once you activate the stem of the three-way valve, you will allow the pressure to go to the right side as long as the stem is pressed. When you release the stem and the pressure is still at the bottom, then all the pressure that was allowed into the system previously will vent through the hole in the stem. This position is not important for analysis of the limited member system, but if the stem is down and the pressure that would try to vent from the system, let's say if you release the pressure from the bottom of the valve, the pressure would travel the same way as it came from. So when you have a stem down, pressure from here goes to the right. And if you reverse the direction of the pressure, from the right would go to the bottom. Only if the stem is up, the pressure from the side would vent through the hole in the stem. Because as you see, if the stem is up, the pressure here is being stopped and not allowed any further. So whether is pressure or no pressure at the bottom in this case, and the pressure coming from the side would vent through the hole in the stem of this three-way valve. So keep in mind all those positions of the three-way valve, because those two valves we are using, and it's important to understand how this valve works in order to analyze our system. Okay. So let's go back to our system. And here we go. So as you see, since the stem is up, the pressure, it's stopped right here, and it's not allowing the system, waiting for the activation of the stem. Since there is no pressure in this part of the system, therefore actuator cannot be activated, and the stem inside the actuator is also up. So the pressure just waits at the bottom of this three-way valve, and it's not allowed further in the system. So if you look at this stage with the stems up as your initial stage, then you could basically color code this stage as the pressure is coming into the system is indicated with color red. So coming from supply, all this hose coming to the bottom of the first three-way valve is red, and this hose coming to the bottom of this valve is red as well. So the only color coding on this diagram would be this hose is red, red. Since the pressure never entered the system, then there is no blue because there is nothing venting from the system. Blue would indicate that something is venting when the previous stage was red. Okay, so blue indicate venting from previously pressurized parts of the system. Okay, and if it's not clear at the moment, we will analyze the system and you will understand what does it mean venting of the previously or pressurized system. Previously, it means in the previous stage that you analyzed, there was pressure in this part of the system. And right now in the new stage that you analyze, there is no longer pressure being provided to this part of the system. Therefore, this part of the system would be venting, indicating blue. But we don't have a blue because we don't have any pressure previously in any part of the system. So the only color coding of the first stage, which is initial stage, initial meaning before you press any any valves, before you have any activations of any valve, the pressure in the system is as follows. It's coming from the supply to both three-way valves and stops there. So the next logical sequence would be this stage would not change until you do something. It means activate a push button. So let me.
Professor, I have a question.
Yeah, go ahead.
So I guess we would be kind of coloring in to do when we do the analysis, we'd be doing the coloring in of the red and blue.
Yes, you would be, and
Okay.
you would be preparing diagram as well. And just to hold on to your questions about the color coding and stuff, as I finish on the black and white diagram of the pneumatic system, I will switch to already color coded report. So you will have to clarify what the stage means and how many stages you may use for given system, and that would be just kind of guidance. But if you feel you can you will need more stages, you can add extra stage to whatever is in the report I will use for analysis. But you will have definitely representation how the report was analyzed previously, how the system was analyzed previously for the report. And the report that I'm going to use, it's 100 points report, so it's exemplary, that it's very with good analysis. Okay, so does it answer your question, Sam?
Yes, it does.
Okay.
Thank you so much.
Okay, thank you. So the next logical step for the next stage, because we analyze everything in the initial stage. So the next stage is the stage of activation. What you would do, you would press the stem down. So that, let's say, would be the second stage. And when you press it down, you allow the pressure from the bottom of the three-way valve going into this hose and through the flow control. As we mentioned, the arrow on this flow control is pointing to the left. It means that controlled flow is from the right to the left, and from left to right there is a free flow. So at this stage, this flow control does not control the flow. There is a free flow entering into the system as you press down the stem. And note that since when you press the stem, there is a spring inside the valve that if you release the stem would pop up. Therefore, you press the stem and you keep holding on it until we get to the stage when we release the stem. But at this point, we physically activate it by pushing down the stem, by pressing it with our thumb, and we keep holding until we fully unwind what is happening with the system. So the stage 2 activation stage, we press down the stem, pressure is allowed through the right, entering against the direction of an arrow, so it's a free flow entering into the system, and enters into right here into this connector, which split the pressure to the right and to the top of the actuator. Okay, so since the air tank, what does it do? It basically increases the volume of the pressure in this part of the system, not in entire system, only in this part of the system. So by increasing the volume, it takes more time to pressurize or to depressurize the pressure, this part of the given system. Air tank is usually used, the most efficient, when it's used in series with the flow control. So usually the air tank works when it pressurizes or depressurizes, the air is pressurized or depressurized with the direction of the flow control. So this flow control actually controls something. Since the flow control, the arrow points to the left, then pressurizing this part of the system is not being slowed down or controlled by the flow control. So so the air tank does not really control much of the time how quickly this part is pressurized, because there is no controlled flow for the flow control. So this part of the system is pressurized quickly with a minor negligible delay. Okay, and when you pressurize, of course, at the same time, you pressurize the air tank and the actuator. So let's say if an actuator needs, let's say, 15 psi to actually to activate, and also let's say the stem, it's the force of the spring pushing the stem up is about 15 psi. That you need this part of the system to have a minimum 15-20 psi to actually activate the stem in this three-way valve. And once you keep pressing on the first on the top three-way valve, this part of the system, let's say it's already pressurized to 20 psi, activating this actuator and allowing the pressure in this three-way valve to enter from the bottom through this hose on the right. And this is our spring return cylinder. Piston extends. Okay, so just so you see the components, we'll continue on this one. So stage number 2, we press down the stem, pressure enters freely against the flow control. So flow control doesn't control the pressure. Pressure enters this part of the system, splits into the air tank and the actuator. Once it reaches about 20 psi, actuator activates. Actuator activates, but the pressure, of course, continues to build up until is 40 psi, which is the pressure coming from the supply that we set on the gauge. So actuator is activated, pushes down the stem. Pressure right now enters through the bottom of this three-way valve, enters through the hose, pushes the piston out of the cylinder. Okay, so in this stage, what is happening? Basically, the pressure enters into this part of the system. So everything, basically every single hose in the stage 2 is right now red, because you have pressure, of course, remaining pressure coming from the supply, and right now everything is red, and spring return, also piston from the spring return is being pushed and is red. The only small indication of the blue would be in the front of or on the right side of the spring return cylinder, there is a small venting hole. So the only venting is the air venting from the front venting hole of the spring return cylinder. If we didn't have this hole, the piston would not fully extend, because this chamber would pressurize itself with the lack of any opening and the venting hole, and then the basically piston would not fully extend. Okay, but because we have a venting hole, then the piston fully extend, and the air, not pressurized air, but nevertheless some air from the rate chamber vented out and allowed the piston to fully extend. And that's our second stage. And we will have this stage as long as the stem of this three-way valve is activated. Okay, so the next stage would be to release the stem from this three-way valve. So stage number 3, it's release the stem. When you release the stem, what's happening? Then you block the pressure coming from the bottom of the valve, and the pressure that right now is in this part of the system, because the stem is up, it's venting from the right side into the hole in the stem of the three-way valve. Okay, so right now this line is blue because the stem is already released, so air without an obstruction comes right here and vents blue from the hole in the stem. Since the arrow on the flow control points to the left, this part with the air tank, which has a greater volume of the air, pressurized air, due to the installation of the tank, is depressurizing slowly, because flow control dramatically reduces the speed of the pressure. So in this case, we have the air venting slowly due to the flow control. So on your diagram, you could indicate that this is still red, or you could just make like a mixture of blue and red and indicate that stem is already up, the pressure is venting, but it did not depressurize below 20 psi, therefore actuator is still pressed and piston is still extended. So that's your stage 3. And this stage 3 would indicate that when you release the stem, you don't immediately depressurize the whole system because you have the flow control. If you release the stem and you didn't have the flow control, then basically you would say, okay, this is all blue, it's venting, you had the depressurized actuator, and everything is returning back to the initial. But because you have a flow control and because you have the air tank, then you have to focus on the purpose of the flow control and the air tank in this system. What does it do? Therefore, the stage 3 would be that stem is released, you're venting the pressure, but this part is depressurizing slowly, okay? And the piston is still extended. Stage 4, this part already depressurized enough in order for the actuator to release the stem. So right now, all of this is blue. This is still blue, it's continue venting, but because this is already blue, actuator is up, the pressure stopped right there, no longer supplies the hose for the cylinder. So since this stem is up, the pressure that vents from the spring return cylinder, since you have no longer pressure entering the spring return cylinder, right now the spring in the front inserts the force on the piston to return. And since there is no longer any pressure counteracting the force of the spring, then the piston returns. As the piston returns, this is blue right now, this hose. And where does the pressure vent from the cylinder? it doesn't vent right here because there is a pressure being stopped right here. And still, this hose still continues the pressure. So this hose from the supply never changes the color. It's always red. But the previously pressurized part that kept the piston out right now vents exactly the same like here. It vents through the hole in the stem. Also here, it vents through the hole in the stem. And since the actuator is deactivated, at the bottom of the actuator, there is a hole that allows the pressure that vents through the stem, vents farther outside, out of the system. So your stage number 4, it's this is blue, everything is blue, and the piston returns. Okay. So that said, and the system returns to the initial stage when everything is vented out, stem is up, and the pressure is at the bottom of three-way valves, stopped, waiting for another activation of the stem. So stage number 4 is the final stage, and the piston returns inside the spring return cylinder. So what's the purpose after we analyzed the system? What's the purpose of the flow control in this case? What does it actually do? And what does it do in conjunction or cooperating with the tank? So the purpose of the flow control is to slow depressurizing of this part of the system, and depressurizing, slowing the depressurizing of this part of the system. The purpose of it is to create delay from deactivation of the actuator, or the delay in return of the piston inside the spring return cylinder. So when you had the second stage, when you activate the stem of three-way valve, flow control did not control pressure entering the system. So the pressure entered the system quickly, and the moment you press the stem, the moment the pressure activates the actuator, piston shoots out instantaneously. Okay, so this part of flow control with air tank did not create any delay in extension of the piston. The moment you activate the three-way valve, the piston shoot out instantaneously without any delay. But then in the stage 4, when you release the stem, or stage 3, when you release the stem, this part right now is depressurized slowly due to the flow control. And not only is depressurizing slowly, due to the larger volume that it's in the tank. And tank does not increase the pressure in the system. Tank only adds extra volume. So let's say if you have a bucket of water that you can either pour out quickly, and in 1 second your bucket is full, is empty, or you have to clear it through a very small tube. So it will take time for the water to drain out of the bucket, because you have a very limited flow out of this bucket. So of course it will take a long time for the bucket to be emptied. So that's similar idea between depressurizing extra volume from the tank, because as long as there is still pressure remaining above 20 psi, this actuator is not deactivated. So this extra volume creates a time delay for longer activation of the actuator, so the piston remains out, extended beyond the activation of the stem. So in terms of, let's say, timeline, since you don't have the actual experiment, you are not able to do the actual experiment, I would say you release the stem. This part is depressurizing slowly. You have, let's say, 5 seconds time delay. This 5 seconds necessary to depressurize the part to, let's say, 20 or below 20 psi, and then the piston returns. So if you have to analyze the system in a couple of sentences, what does it do? You would say you activate the piston, the stem, pressure enters the system quickly, piston shoots out right away. Then you release the stem, the pressure from the system is venting out slowly. After 5 seconds of time delay necessary to depressurize the system enough to deactivate the actuator, piston returns. So you press the stem, piston shoots out right away. You release the stem, you have 5 seconds time delay, and the piston returns. Any questions about analysis of the system before we move into the report when there is a color coding? Okay.
I have a question.
Go ahead. Go ahead.
Yeah. When the piston returns, is it slowly returning as the chamber depressurizes, or is it
Yes.
once
As
it
the left,
depressurizes, it goes back in?
as the left chamber depressurizes, because there is no longer pressure coming from the bottom of the three-way valve. Because when you depressurize top of the system, the actuator goes up, then the stem goes up, so the pressure stops at the bottom of this three-way valve. So as the pressure stops, there is no longer pressure coming into the right, and right away the stem is up. The pressure that was provided to the right now vents right away through the hole in the stem of three-way valve, which is inside of the actuator, and there is a little hole in the actuator which allows further to vent the pressure out of the system. So is it okay? Like, did it answer your question?
Yeah.
Okay. Okay. Then, since we analyzed that flow control with the direction to the left creates delay in the return of the piston, it does not create delay in extension of the piston. Then what would happen if by mistake you would put the flow control in the opposite direction? It means the arrow would be pointing to the right. Does anyone has idea what would happen if your flow control was reversed and actually your knob was to the left, so the arrow points to the right? So the controlled direction is from the left to the right. How differently would the system work? Okay, so the difference would be that right now when you press down the stem, you allow the pressure coming, but because the arrow points to the right, pressurizing of this part of the system is slow. So right now you have to wait until this tank and the actuator pressurizes to the minimum of 20 psi to activate the actuator. So from the moment when you press down the stem, the pressure is building out slowly, then eventually activates the actuator and the piston shoots out. So in terms of action, you activate the stem, you have 5 seconds, let's say approximately. Let's keep it standard with the release. So you have 5 seconds time delay, and then the piston shoots out. When you would release the stem, then since arrow points to the right, the pressure is being depressurized without control of the flow control. So it's depressurized quickly. So the moment you release the stem, pressure bends very quickly and the piston returns right away. So with the flow control pointing to the right, you would have delay at the extension of the piston, and you would have fast return. With the flow control as we have, meaning arrow points to the left, you have fast extension and you have delay on the return of the piston. Okay? So this is, you could include it in your report of what's the purpose of the flow control and the air tank, because that's crucial for analysis. What's the purpose of the flow control and the air tank? Once you analyze it in this system, then if you have a similar setup in other systems, you don't have to go there because you already have the analysis. But this setup of flow control and the air tank, it's the important introduction of how can you create a delay in activation or deactivation of certain parts of the system. Because in this case, the system is simple, so basically it affects the whole system. But sometimes a system is more complex and you want to delay activation of one part of the system. So there's some delay, then after the delay, it's activation of the second part and so on. So your system is activated in stages. Okay. And I will stop sharing this lab manual. So we will go to see the system analysis. And I'm just going to check that. Fernando, I marked you present. Let me just, so welcome to the class. Just if you, since you logged in later with some kind of delay, if you have any questions about analysis of the first system, I'm recording this session, so I can forward you the link. Just send me an email. I will not be sending to the whole class unless I will receive a lot of inquiries. But send me inquiry first. I will see how many people were unclear, and that will give me also an idea how clear it's are the analysis, so you don't have to go. So I may focus more on analysis. Okay.
Okay, thank you, Professor.
Sure. Let me just stop sharing that. And just give me 1 sec. And here we are. Okay. So, for example, you have this report. So beside the front page, when there would be your names, name of the report, meaning pneumatics, and your group number, which I will assign later today. The second page is table of contents. So once you divide the work between yourself, which system everyone prepares, then once your parts are ready, you put them into the report, and it would be great if you could specify what's the page number for given parts. And it's great if you put the parts in chronological order, so in order of how we analyze it. So our systems that we have are limited memory, full memory, one cycle and reset, CAM cycling, so on, and then your project design. So your own system, which we will analyze like in 2 weeks, so you know what's the outline and requirements for your own project. So limited memory, you see, is on page 224. And the next page would be objective. What's the objective of the entire topic? So what's the objective of pneumatic system, of building them? Okay, and here's the limited memory system. So I will not go through analysis. I will just analyze again with you, and this will be just brief analysis to show what is happening. So here is the stage 1, your initial stage. And as we mentioned, the pressure is only read coming to both three-way valves. And you see over here, that's MAV3 valves, number 1 and number 2. So as I told you, each component has a unique number. So even though number 1 and 2 are both MAV3 valves, they don't share the component number. They have a unique number. So right now you can clearly start analysis that you activate number 1, and you know that number 1 is MAV3 three-way valve. Okay. Also on your flow control, there is an arrow. Arrow indicates the engraved direction of this flow control, in which way the flow is controlled. So you see, if you allow the pressure from left to right, it's not controlled. The controlled pressure is only with direction of the arrow, so it's from the right to the left. Okay, so here, initial stage, the pressure here. The next stage would be activation of the stem of number 1. And let me go through those analyses, so you at least have some idea how it was analyzed. So the limited memory system, the piston extends when you press the push button and returns when it's released. So it's kind of, you start with conclusion, but you specify in short how it's supposed to work. So it tells you initially the supply pressure travels up to valves number 1 and 2 and stops there. That's short, 1-sentence description of the initial stage, and that's all you need. Okay, stage number 2. So you press down the stem of number 1, the pressure fills up quickly, activates the actuator, allows the pressure into the spring return cylinder and the piston shooting out. And you see this little opening in the front, that's the only blue part, because pressure bends out of the system by being by the left chamber being pressurized and pushing it out. So if you read the short analysis, is when the push button number 1 is pressed, pressure travels freely through flow control. So you see it indicates that it travels freely through the flow control. So it's not controlled. And then into tank number 5. After the tank is filled, the pressure travels to actuator number 3 and activates number 2. So that's not exactly that tank has to be filled before the actuator, but in general, that's what it works. Since the tank, it has much larger volume, it has to be filled up or pressurized in order to activate the actuator, which activates valve number 2. So you see, you easily refer to the valves without saying 3-way valve, 4-way valve, and everything. You just say travels to actuator number 3. Okay, so you may just indicate travels to number 3, but it's fine if you use the actuator number 3, which activates valve number 2. So in this case, you don't have to indicate that that's a 3-way valve. This allows supply pressure to travel through number 2 and extends the piston. So quick extension, indication that there is a free flow through the flow control. So it's a quick extension of the piston. Then here you see, when I analyzed it, I used 4 stages. So stage number 3, this part was venting, but this part was still pressurized due to the flow control. But if in your analysis you describe what I described in stage 3, then your stage 3 would be your final stage. So let's see what they describe. When push button of valve number 1 is depressed, flow control number 4 limits the amount of air exiting tank number 5, which delays the return of the cylinder. Okay, therefore adjusting the setting on the flow control changes the delay with which the piston returns. Okay, so this is sufficient to skip one stage. But if you would choose to add extra stage number 3 and 4, as we analyze, that's absolutely up to you, the best way of how you want to fully describe the system using the four stages. Okay, and they didn't indicate here the amount of the time delay, but at the same time it depends on the flow control, how much flow control is open. Also, in order to, in this case, to increase the delay in return of the piston, as indicated in this analysis, adjusting the setting of the flow control changes the delay. So if you open the flow control, delay could be shorter. If you make the flow control tighter, the knob on the flow control tighter, the delay would be longer. Also, you could adjust the time delay by installing a different size of the air tank. As you've seen when we reviewed the components, there are many different sizes of the air tanks. In the lab, we had MAT10 and MAT50, where MAT50 was 5 times a larger volume than MAT10. So if you want to increase the time delay, you could either open or close the flow control. Opening would decrease the delay, closing would increase the delay, or you could install the larger size of the tank, which would increase the delay, or you could install the smaller volume of the tank, which would decrease the delay. Okay, so those are the ways of controlling the delay in your system by installing the appropriate size of the tank, so you have a larger volume or lower volume, and adjusting the flow control. Changing the direction of the flow control would completely change the way that the system works, because changing the direction, as we mentioned, would create the delay in extension and no delay in return. Therefore, you cannot use it as adjustments of the delay in the return. the delay in the return would be controlled only by adjustment of the knob on the flow control and and installing larger or smaller volume of the tank. But flipping the flow control would completely change the way the system works. Very good. So I think,
Professor, I have a question.
go ahead.
So for the actuator, number 3,
Yes.
I know you said earlier that it actuates when there's a pressure greater than 20
Yes.
psi.
Yes.
So, when it's venting, does it instantly deactuate when there's like less than 20, or does it gradually?
No, it has to be less than 20 for the actuator to deactivate. If it's still
Okay.
20 or more, actuator is fully pressed and the stem is down and the piston is still extended. So basically, what it happens is once the pressure in this part of the system drops below 20, the actuator deactivates, stem moves up, and piston returns quickly. So it's not like the piston moves slowly in. It just, there is this moment, like a tipping point, when the pressure does not activate actuator anymore. Therefore, actuator just deactivates, stem pops up, and piston returns quickly. So there is not, so flow control and the tank does not slow down how the piston returns. Piston will return in slowly the moment this part is depressurized below 20. Okay, it just creates the delay from the moment when you release the stem to the moment when you see the piston returns. But the piston will return quickly as soon as this part is sufficiently depressurized. Okay.
Thank you so much. Thank you.
Very good. So I think we're done with this system, and it took us a while for the first system because we still have to like remember all the components, how they work. Hopefully the next system will be a little quicker as you get more experience with analyzing it. But I wanted to go through the diagrams to indicate that each component has a unique number, table of components, and then you refer to those components in your analysis. So you don't have double or triple describe them, but you have the description in the table as the model number and what type of the valve. And then when you do analyze, you just use the number 1, 2, 3, 4 in your analysis. And since each component has unique number, you don't have to indicate three-way valve from the top, three-way valve on the top, on the bottom, or right or left, but it has a unique number. Okay, Thierry, do you want to ask something? I see that you raised the hand.
Did you post those files too, or that's what we got to do the lab report?
Again, could you repeat the question?
That's the example to do the lab report, right?
Yes. The one that I'm using. Mm-hmm.
Yeah. Okay. Thank you.
I didn't send it out to you. I'm using it only for analysis. Okay.
Oh, okay.
So you have a template of how to use it, but I'm not sending you because that's your work, and you should use your own words and your own diagrams.
Okay.
Okay. Very good. So let's go back into the second system, and we share it. Okay, and here we go. And the second system is on page 11. So page 11 is a full memory system. So take a look at it for a second. If you want, you can have a sip of water or something like that. And I will be back like in 1 minute. Okay. And here again, in the system, you know, you don't have a table of components, but you should understand that you should follow the same pattern as you've seen in the lab. Each component should have a unique number. You should have a table of components, and so you understand what components you use and how to refer to them easier by using the unique number. Okay, so before we go into analysis, it's like, let's see what the system is. You have a pressure coming from here, and this pressure is split 3 ways. So it goes to the bottom of this 3-way valve, the bottom 3-way valve, and goes into 4-way valve, and this is MAV4D. So that's a 4-way valve with 2 stems, and on the top of both sides, so over both stems, there are 2 actuators, MPA and PA. The 4-way valve is connected to double acting cylinder. So the top threaded opening goes to the back, to the left side of the cylinder, and the bottom threaded opening from the 4-way valve goes through the right chamber of the cylinder. I will stop sharing this, and I will put on the pneumatics handout to show you how MAV4D works. So you can go through the stages of how the pressure travel through this system. But I just want you to see that when you analyze, right, before we had only one push button, so there was no question what does it mean activation. Since you have 2 push buttons right now, how do you activate? Do you activate one at a time? Do you activate both at the time? So in order to clarify, you will analyze activation of one push button at the time. You don't activate what would happen if you press 2, because frankly it doesn't make sense to activate 2, which would activate 2 actuators at the same time. So that could be kind of like locking down the system, or the system would not change because whatever was the previous position of the stem, it would still remain. So we will activate one push button at the time, and when you release, you analyze what happens when you activate the other one. Okay, so that said, when you look at this diagram, let me go into the handout. Okay, and now you should see that's a 3-way valve. Let us go to the 4-way valve. Okay, and that's MAV4D. So this valve is in the position that we actually have on our diagram in the lab manual, and you have the pressure. This pressure on the diagram, it's all the time supplied to the 4-way valve. So since the pressure is always on the left side, coming from the source, then whether the pressure goes up or down will depend on the position of the stem. So let's look. if the stem is up, the pressure comes through the top. If you press the stem down, the pressure goes through the bottom. Okay? If the stem is up and you would reverse the direction of the pressure, it will be established the same like in our previous case. But if the stem is up and the pressure would be coming from the bottom opening, it would go directly through the venting hole. Okay? Since you see, it makes sense if the stem is up and this pressure path is already established regardless on the direction of the pressure, then anything from the bottom is right now separated right here by this piston inside the four-way valve, and the pressure could travel only through the bottom. Similarly, when the stem is down, you establish the pressure coming from the pressure source into the B. If you reverse the direction of the pressure, this part is already established. So this part of the system is separated by kind of like a stem inside of the valve. So if the pressure would be coming from the threaded opening A and the stem is down, this pressure would be venting through the top venting hole. So this is just reminding how the valve MAV4D works. And right now, let's stop sharing it. And we will go to our diagram. Okay. So just take a little look and have an attempt of actually analyzing the system yourself, if everything seems right. Because this diagram was prepared for the students who actually built the system, the physical system, by themselves. So if they build the system, I would approach the bench and say, so how does the system work? And say, yeah, it's work fine. It works exactly as on the diagram. And they said yes. So I want you to find out by looking at the system and by looking at the MAV4D valve and see if it actually works the way as on this diagram, that when you press the top three-way valve, the piston extends, and when you press the bottom valve and this valve is up, the piston would return. So I want to give you a couple of minutes of actually trying to analyze the system before I analyze. And this moment of doing your own work, it's very important, because then you start thinking how it works. You don't have someone's guidance or my guidance to go through analysis, but you do the first attempt of your own analysis. So for 2 minutes, analyze what would happen if you press down this valve. You will open the pressure and send it right here. You will activate the actuator. By activating the actuator, you push the stem in the four-way valve down. If you push the stem down, where does the pressure from here goes? Does it go through the top or through the bottom? And what happens to the piston inside double acting cylinder? Does it extend or doesn't return? Okay, I will give you 1 minute and then we will go back to the diagram. If anyone wants to start telling, you know, their observations, you're welcome to unmute yourself and add your comment. If you don't feel like you want to add, you can wait and I will go over it. Okay, so let's go back. If this diagram is correct, so when you press down the tap valve, you send the pressure, which activates this actuator and pushes the stem down. When we look at the diagram of the four-way valve, we notice that, okay, so right now you see the stem is down. Okay, so where does pressure goes? Goes through the top or through the bottom? So let's again look at okay, just give me 1 second and okay, so the stem is down because we activated the top valve and we push the stem down. So see the pressure coming from the source goes through the B, okay? So let's see on the diagram, how does it refer to our diagram, if that's what it is. You see, when we press down, the stem is down. In order for the piston to extend, you would need the pressure coming from the top opening. And we know that when we press down this valve, the pressure is coming right now through the bottom. So actually, the piston is returning, okay? So right now you have right away, but by knowing how the four-way valve MAV4D works, you have a proof that that this indication that the piston is moving out right now is incorrect, because when you activate this valve, you move the stem down. When the stem is down, pressure goes through the bottom opening and fills up the front chamber, so, or right chamber. So if you fill up the right chamber, it would create a piston to return, and as the piston returns, the pressure from the left chamber would vent through the venting hole because the stem is still down. So any pressure coming from here would vent through this venting hole. When you activate the bottom push button, then you provide the pressure, and then basically you move the stem up. As the stem moves up, the pressure from the source goes through the top. So if the pressure moves through the top, then it pushes the piston out. As the piston is moving out, the pressure from the right chamber comes right here, stem is up, so the pressure from here vents through the venting opening at the bottom. Okay? So please indicate in your notes that this page 11, it's misanalyzed, okay? And it's not misanalyzed because it's something that was by accident. It's misanalyzed to assure that the students do their own analysis. And you know, it's like, even though I point out at this, some students don't have notes and they still submit their report with this mistake in their own analysis because they don't trust their own analysis as much as something that is on the, let's say, on official handout or documents. It's like, yes, the handout is important and the lab manual is important, but this is one page that kind of push the students to do their own analysis because they build the system and they should analyze the system, and they have the handout with the description of valves, how they work, and they're supposed to be able to catch this discrepancy of how the system works. So when you activate the tap, the pressure at the stem is down, pressure comes here. So the tap valve returns the piston. Activation of the bottom valve pushes the stem up and extends the piston. So here the tap valve return the piston, the bottom valve extend the piston, exactly opposite as on those two diagrams. Okay, with regard to the color coding, initial stage, before you press any valve, so let's say both stems are up. If both stems are up, pressure from supply comes here, and this hose is always red. So regardless on the position of the stems, or if both stems are up, this hose is always red because it comes directly from supply. The question is, if both stems are up, the pressure doesn't stop here. It goes depending on the position of the stem, whether stem is up or the bottom. So in such a case, you should pick what's the initial stage of your piston. Is your piston in or out? Let's assume that you start with piston being in and both stems are up. If the piston is in, it means the pressure has to come from here, okay, from the bottom. If the pressure would be coming from the left side, piston would be out. So if in the initial stage the piston is in, then this hose is red as well because it keeps the piston in. So if this hose is red in your initial stage and those hoses are red, those are neutral. It means no color. No color because there was no pressure before, and this is your initial stage, so you cannot you don't have any venting. But if that is your initial stage, that this hose is red, red indicates that the stem is at the bottom. So your second stage would be automatically pressing up this push button, because this push button would move the stem up. If this is your initial stage with this hose red, and then your second stage would be activating this push button, it wouldn't make much sense because the stem is already down. So activating this push button would activate this actuator, but would not change the position of the piston. Therefore, it's much better if after initial stage, if you choose the piston to be in the initial stage, then the second stage would be pressing down this push button, pushing the stem up, therefore extending the piston. And stage number 3, once the piston is extended, you activate this push button to push the stem down again, and then the piston returns to the initial stage. So I think 3 stages would be sufficient. And let's go right now to our lab manual to find out what's how the system was color coded. Okay, here we go. So that was the first system, full memory system. Okay, so this is your actually initial stage, but they skip initial stage as both stem going up or pointing up. And they right away indicated that the bottom or valve number 2 is activated. And once again, you see each component has a unique number. There's a description of model number, what type of the component, and so on. So you can easily relate to it. They even have the indication of A and B, which is actually engraved on the valve. So you can relate whether the pressure go through opening A or B, but you could also describe it as top and the bottom. So you see this hose is all red because it's pressurized all the time. There's no way to depressurize it as seen on our diagram. And if you press the push button at the beginning, this moves the stem up and the piston extends. So valve number 2 responsible for extension. Stage number 2, when you activate valve number 1, you move the stem down. As you move the stem down, the pressure is switched from B, piston returns. As the piston returns, the pressure from the left chamber leaves right here through the venting. And in the meantime, since this valve was previously activated, all the pressure that was provided to number 4, you see, you released it. So since this previous stage, this hose was pressurized, then it's being shown that right now it's venting. What I would add to it, I would add the third stage, which indicates that when you release this stem, all this pressure from this hose will be also vented through the stem. This is not a big mistake. They could just limit it to 2 stages and just describe that when you release number 1, the pressure vents through the hole in the stem. But you have a choice of adding up the stage as well. Okay, any questions about this system? If you have.
I have a question.
Sure.
What would happen, I guess, if both 1 and 2 are pressed? Would that
Okay.
just depend on the state it was in before?
That's correct. So let's assume that you have this stage 2, and right now you press number 2. So you keep number 1 being pressed and you press number 2. This stem is already down and is held down with the activation of the actuator because the actuator has a pressure on this side. So if you press number 2 and you provide the pressure is provided to the actuator, but it cannot actually activate the stem because it's the equal and opposite pressure on this actuator. So the piston, nothing would change inside the valve because you have the equal and opposite pressure on the other side. So pressing the second valve once one valve is still pressed is not going to change the position of the stem in the valve, nor the position of the piston in your cylinder.
Okay, so it would still, so you'd feel kind of the pressure in that number 2, or would it like vent through the actuator?
No, if you activate number 2, you would pressurize this hose and this actuator would get pressurized, but it would not get activated because activation of this actuator would be prevented by the stem being firm, extended. So you cannot, your actuator would try to push on the stem, but the stem it's forcibly kept in one position and cannot be cannot change the position, cannot be reactivated. Okay.
Okay, got it. Thank you so much.
Okay, so right now we analyze the first two systems, and we will have the time to analyze one more. But before we move to the third system, what's the difference between full memory and limited memory? Why is the first one called limited and this one is called full memory? Okay, so you see that if you activate valve 1, you activate the actuator 3 and the piston returns. Okay, if you release the stem, the piston will still be in and remains in its position. So the last activation was number 1, which sent the command of return the piston, retract the piston, and the piston stays inside the cylinder. If your command was activating valve number 2, this valve number 2, it commands for the piston to extend. If you release this stem, the piston remains out. So this indicates that your command, it's being remembered. So it's a full memory. Activation of number 2 indicates extension. Activation of number 1 indicates retracting the piston. So unless you would activate number 2, you know, the piston will stay in after releasing down the stem. If we go into our limited memory, then you will see that activating the stem extends the piston. So your valve number 1 sent the command piston out, but after some time delay, a few seconds time delay, when you release the stem, the piston returns. So it's kind of, you know, indicating that you activate number 1 to shoot the piston out, but after you release the piston, there is some time delay and kind of system doesn't remember the last command and return to the initial stage of the piston retracts. So that's why the first system is called a limited memory, because the activation is limited only for a few seconds beyond the release of the stem. The moment you release the stem, it's the memory of the command, of the last command of sending the piston out is limited to a few seconds. And after a few seconds, piston automatically retracts to the initial stage in. So that's why this is called limited memory. And this system is called full memory, because activating the valve clearly indicates piston out, piston in, and remains out or in as long as you activate another command. So this one is called full memory. Questions? Okay. So that said, let's go to the last system we will analyze today, which is one cycle, then reset. Okay. And let's go first to our lab manual. Okay, you should have it on your screen, and we will go to the actual diagram. Here you go. And let me rotate it. Okay. So one cycle, then reset. You have a table of components. And in this system, for the first time, every component has a unique number. So it is as it should be. And let's do analysis. The name indicates it's one cycle, then reset. Your components are number one is MAV4D. The pressure comes from the supply, from the site. So we had MAV4D already in the previous system in a full memory. In this case, actuator is attached only on one side. So pressure will reset this valve, but the original initiation or activation is done through the manual pressing on the stem. And you see number 7 indicates push button. Push button is just a fancy way you put a little cap on the top of the stem to have it like a physical push button. But in the lab, we never put anything on the top. We just activate the stem. We push the stem. Okay, so that's what you have. And initial stage is when the piston is inside. So since the piston is inside, and you know that from supply, the stem originally is up. So if the stem is up, the pressure from the supply goes where the stem is. So goes through the top, comes right here, and fills up the front, the right chamber of the cylinder, keeping the piston inside. If you see at the direction of the flow controls, both flow controls number 2 and 3 are pointing down. I'm not sure if it's as clear, but the both arrows are pointing down. That's just a little indication. And if the arrow doesn't show you clearly, you look always at the position of the knob. So if the knob is to the top, it means arrow points down. The knob is also at the top, arrow is pointing down. So if the arrow is not very clear, where does it point, then basically you may be sure, you can confirm by looking at the position of the knob on given flow control. Okay, so we have our initial stage when the pressure is here and goes through the hose, through the flow control, and piston is kept in. First, we'll analyze the system, and then we analyze what's the purpose of the flow controls and what part of the system given flow control, or which stage the flow control number 2 controls, which stage number 3 controls, whether they control the same stage or different stages. And stages meaning, does it control extension, does it control the return, and how does it control the extension or the return of the piston. Okay, so our initial stage, very simple, and since we have only one activation button, which is a push button, or stem number 7, then what we will do. So when you press down the stem, so the stem is right now at the bottom, the pressure is being switched from the top to the bottom. All the pressure that was previously coming through the top, right now it opens the venting path through the venting hole at the top of the left side of the MAV4D. So all the pressure from the right chamber and from this hose is right now venting, and the pressure from the supply is redirected through the bottom thread and comes right here, provides the pressure to the left chamber of the double acting cylinder, and continues and splits 2 more ways to go to the bottom of number 4 and number 5. Since the piston is right here, and those 2 ports are the cam followers, number 8 and 9 cam follower, and they are in up position, they will be down only when the piston actually it's pushing on them. So at this moment, when the piston is still inside, both cam followers are not activated, therefore the stems are up, and the pressure just waits at the bottom of number 4 and 5, waits kind of for activation of the cam follower. We have another cylinder, which is components. Cylinders are the components which indicate the output, and you analyze the whole system by looking what's the reaction of the piston in the either double acting cylinder or spring return cylinder. Therefore, since the pressure comes right here to the left chamber of double acting cylinder and waits at the bottom of 4 and 5, so 4 and 5 are ready to allow the pressure through their left side as the cam follower is activated. But at the moment, the pressure that goes through number 2, it's right now beginning to extend the piston to the right. Okay, so that's our second stage. As the piston is moving forward and right now activates cam follower number 8, that's our third stage. Third stage is when the piston, it's resting or it's pushing number 8. Therefore, stem of number 4 is pressed and the pressure is allowed right here into this hose, and the spring return extends. That's our third stage. Our fourth stage is the piston, since the pressure is still to the left, it continues to move to the right direction. So as the piston is moving forward, is at this stage, is between 2 cam followers. So the pressure, right now this cam follower is not being pushed on the piston, so it pops up, because only when this kind of sphere that is attached to the top of the piston, it's resting on it, then the cam follower is being pressed. But as soon as this sphere is in between the cam followers, this cam follower pops up, the stem is up, therefore pressure from the spring return cylinder comes right here. There is still pressure at the bottom, but this pressure from the side, from the left side, vents through the hole in the stem, meaning the piston from the spring return cylinder, it's retracting fully back into the cylinder. So spring return cylinder already completed 1 full cycle. And this piston continues its path to the right. So stage 4 that we just described, piston is moving forward, is between 2 cam followers, and this is venting. So this hose is blue and vents through the hole in the stem. Stage 5, the piston is right now resting on number 9. So it's fully extended, activated the cam follower, therefore pressing down the stem and allowing the pressure right here through this hose and activating the actuator number 6. So all this hose is red. It's red coming right here and activating number 6. Activating number 6 will push the stem up to the initial position, which was originally started with when the stem was up. So since that was number 5, number 6 is the stem is up. Okay, so when the stem is up, it means the pressure is no longer coming through the bottom hose, but is only at the top hose. So if the stem is up, all this hose is venting. So the pressure from the left chamber of double acting cylinder is venting. The pressure from the bottom of number 4 and bottom of number 5, everything is venting. The pressure that activates the actuator, it's also venting through the hole in the stem, okay? So the pressure that actually moved into stage number, I believe 6, it's venting through the hole in the stem. The pressure that activated the actuator that came from the bottom of the valve, it vents right here through this venting hole, along with the pressure that was in the left chamber, which also vents through this venting hole. Since the pressure was switched to the top, right now the pressure red is right here and causes the piston to return. So the piston is returning and the left chamber, it's all venting as the piston is returning. So this hose is blue along with this hose, and this hose as well. What about the hose from the spring return? The hose from the spring return is neutral because venting could take only one stage. So in the previous stage, this piston was already in. So this cannot be venting. The venting stage could occur only for one stage. So only if previously in the previous stage the hose was red, then in the next stage it will be blue if there is no longer pressure supplied to this hose. Okay, so the piston returns and the piston returns to its original condition or initial stage. The stem is up and the pressure is right here only in this hose, and once the piston return, everything else, it becomes neutral. Okay, so what you see, if you have to kind of describe what is the action of how does this system work, you would say you activate the stem, number 7, pressure switches from the top to the bottom, extends the piston. As the piston of double acting cylinder moves forward, it activates number 8, which allows the spring return to extend. As the double acting cylinder piston is moving forward, it clears number 8 cam follower, which allows the spring return cylinder piston to return. As the double acting piston is fully extended and activates cam follower number 9, number 9 pushes on number 5, which sends the pressure to activate the actuator number 6, which resets the stem in MAV4D or the stem in number 1 to push it back up and switches the pressure from the bottom to the top, causing the double acting piston to start its return or retracting path, and piston returns. As the piston returns and activates number 8 again, Do you think that the spring return is going to extend for the second time? So, yes, could you repeat that?
No.
Okay, so yes, you're correct. Nothing will happen when the piston of double acting is returning and pressing on 8 again. You remember that in order for the piston of double acting to retract, you need the pressure at the top. In order to activate the valve number 4, you would need the pressure at the bottom of number 4. And all those hoses that lead to number 4, number 5 are already venting. So there is no longer pressure. Therefore, piston of double acting is just pushing on cam follower, but there is nothing to activate because there is no pressure. So the piston fully returns to its initial stage. Okay, Dario, I will show the schematic of the systems shortly. Before I do that, I want to talk about what's the purpose of the flow controls, number 2 and number 3, and what do they control. So since you see that the arrow points down for number 2 and the same down for number 3, you see the direction of the controlled pressure of number 2 is only from the top to the bottom. Therefore, what do you control? When the pressure enters from number 2 from the bottom to the top, it doesn't control. So number 2 doesn't control the extension because the pressure for extension enters against the direction of an arrow. But when the piston returns, then the flow control controls how quickly the pressure bends out from the left chamber. Therefore, number 2 controls the speed of the piston, double acting return piston returning by controlling how quickly the left chamber is venting out in order for the piston to return. What about number 3? If you provide the pressure from the bottom to the top to the right chamber, you provide the pressure against the direction of an arrow. So this pressure would cause the return of the piston. So number 3 does not control the return. But when the piston extends, by having pressure coming right here to the left chamber, all the pressure from the right chamber has to vent out, and it vents out through the number 3 with the direction of an arrow. So number 3 controls the extension, the speed of extension of the piston by controlling how quickly the right chamber is being vented through the flow control. So having a flow control pointing both down, we analyze that number 2 controls the return of the piston and number 3 controls the extension of the piston. So by adjusting the knob, and you see that there is no air tank here, so flow control fully controls pressurizing or depressurizing. But actually what it does, those flow controls, neither of them controls pressurizing. Both of them control venting or depressurizing. By number 2 controls the return by controlling how quickly the left chamber is being depressurized. Number 3 controls the extension of double acting cylinder by controlling how quickly a right chamber depressurizes, allowing the piston out. So you could include it in your report to specify the purpose of the flow controls is to control, number 2, control the return, number 3, control the extension by controlling venting from appropriate chambers, okay? And keep in mind that you could change what the flow control controls by flipping any of the flow control. So you can go there and try to analyze what would number 2 control, which part of the extension or return, if you flip it. If you had the arrow pointing up, then basically you would control the pressure entering the left chamber. Therefore, number 2 would start to control the extension by controlling the pressure. And if this number 3 would remain the same, then basically both 2 and 3 would control both extension. 2 would control how quickly the pressure enters the left chamber, and 3, how quickly you depressurize the right chamber. So both of them would control extension. Then none of them would control the return of the piston. Okay, so it's really important the direction of the flow control or direction of an arrow on the flow control in the systems. Any questions? 1, 6, 7, 1, 6, and 7 controls pressure. Okay, never mind. No, they do not control pressure. Only number 2 or 3 control how quickly the pressure, the chamber is depressurized from the back or from the left or from the right. Okay, very good. Okay, so let us go to 1 cycle and reset using the lab manual. Here you go. 1 cycle then reset. Initial stage. Pistons inside, the stem is up, pressure from supply goes through the tap, keeps the piston in. Nothing happens until you activate the stem of number 1. Stage number 2, you activate the stem of number 1. By pressing it, you switch the pressure. The pressure that was in initial stage in the right chamber of double acting cylinder right now is venting out of the system. The pressure is right now coming from the B opening, so it's entering right here, the left chamber, causing the piston to extend. And as it extends, it activates. So you see that they conveniently did the stage 2 and 3 that I described in one stage, because this already started to extend and activating the number 7, pushing the stem of number 5, and allow the spring return piston to extend. And you see, as it's extending, there is a venting in the front. So it's beautifully described of how the piston from the spring return extends. Stage number 3, as the piston continues. So you see, they skip the middle part. So step 3 is right from activating number 5, you're activating right now number 6. So as you activate number 6, this cam follower number 7 is already up, and you see that spring return, piston from spring return already returned, and all this air, it's venting through the hole in the stem. Okay, activation of number 8 pushes the stem of number 6, and right now this actuator is being activated, but it had not get activated yet. Okay, but it's already pressurizing, and in the next stage, number 2 is activated and will push the stem up. So stage number 4, the stem was pushed up, so the pressure switched. Right now the pressure comes through the through number 4 into a right chamber. Piston is right now returning. Okay, so actually this is the mistake. The arrow supposed to be, this was out, but right now it's in. Piston is going in, so that's a little mistake. So piston is moving back, but you see the spring return cylinder, there is no venting anymore. The pressure was in previously, this was venting, and venting could take only one stage. Since there was no pressure provided, there the next stage, this part is venting. It is not venting, it's neutral. It has no color. But since this hose was activated previously, then this hose vents through the hole in the stem, and all those both hoses that pressurized number 5 and 6 and the left chamber all vent through the venting right here through the B opening and outside of the system. So let's say, oh, and there is a stage number 5. So as you see, this everything is venting, and your final stage, when everything is vented, it's all in, and right now no more pressure right here. So you go back to the original stage. This actually, if the piston is fully in, then they indicated that at the last moment this part is venting because piston fully returned, and as it's fully returned, this part is also venting. But eventually the initial system is without this blue because everything vents, and your initial stage is going to be just like that. Okay, any questions about the system? Yeah, go ahead.
Question. Yes. Are
Raymond?
you gonna?
Mhm.
Yeah. Are you gonna upload the PDF file so we can read it also?
Okay, let me just